This example is different from the last three in one main way. In the previous examples, we've known either the horizontal or the vertical speed of an object in isolation. And we've had to go and we've had to determine the angled speed or the angled displacement as we need. In this case, we have actually been given the speed on the angle that this golf ball has been struck. So the golf ball is going 42 meters per second at an angle of 32 degrees above the horizontal. What we need to find first of all is the horizontal range. So how far this golf ball traveled. In order to do that, we first need to know for how long the golf ball is in the air. And to do that, we need to know how fast the golf ball is rising vertically. So in a way, we need to reverse engineer the way that we've done the previous examples to break this down, in this velocity down, into its horizontal and its vertical components. So to find the velocity of vertical, we can use SOHCAHTOA again. The velocity that we're trying to find the vertical would be the opposite, and the 42 meters per second would be the hypotenuse. This angle here, again, is the 32 degrees. With opposite and hypotenuse, we can use sine. This time we know the angle. So sine of 32 degrees equals, I'm going to call that side y, and hypotenuse is 42. Calculating out sine of 32 degrees, it's 0.52992. Cross multiplying, going to 2 sig figs, we get 22 meters per second, and that is in the upward direction. I don't quite have enough space to put it on the triangle, but I'll just draw it in here. So now that we know how fast the ball is traveling vertically once it's hit, now we can go about and figure out how long it's in the air. Just on the left here, I'm just going to draw out the basic path of the golf ball. It's going to leave the ground, go up for a while, hit a peak, and come down. Now, as with some previous examples, we cannot deal with this whole horizontal motion at all. We're going to deal with the vertical specifically. And again, we still can't deal with all of it, but we can deal with half of it. What we know is that the VI, when the golf ball is struck, is 22 meters per second up. We know, because we're talking about the vertical component, that the acceleration is due to gravity at 9.8 meters per second squared down. And again, we need the same direction, so I'm going to change G to negative 9.8 meters per second squared up. And since we're only dealing with half of the motion, the final velocity of this ball, when it hits the peak of its flight, would be 0 meters per second. As I've said, we need to find the time that this ball is in the air before we can find how far it goes horizontally. Looking at these variables, we can use VF equal VI plus A delta T. Substituting in, we can subtract the 22 Dividing by negative 9.8 and going to 2 sig figs, we get 2.2 seconds. However, that is just for the ball going from the ground to the peak of its height. For the ball to get back down to the ground, we'll take another 2.2 seconds. So the total time of flight of this ball is 4.4 seconds. Now that we know the total time of flight, we can go and find how far this ball travels horizontally. To do that, though, we do need the speed that the ball is traveling horizontally. So we need the other component of that triangle. So I'm just going to flip to a blank page. We'll draw the ball's flight on one more time. We need how fast the ball is going horizontally. Again, it's a right triangle. SOHCAHTOA, that angle's 32 degrees. We're looking for the adjacent side. 42 is the hypotenuse, so cosine's the best choice here. Substituting in, theta's 32. Adjacent we'll call x. Hypotenuse is 42. Doing cosine of 32, 0.84805. Cross multiplying to 2 sig figs, we get 36 meters per second horizontally for the ball. End of this question is finally in sight. Knowing that the horizontal component of any projectile motion, that velocity is constant, we know it's going 36 meters per second horizontally. We know that it took 4.4 seconds to hit the ground again, so we can deal with v equals delta d over delta t. V horizontally, 36 meters per second. Delta d is what we are trying to find, and the time is 4.4 seconds. Cross multiply, go to 2 sig figs, we get 160 meters that this ball flies. Question B, what is the maximum height that this ball gets to? So now we are dealing back to strictly the vertical component of this motion. We know we found the VI in the vertical direction, 22 meters per second. When the ball gets to its maximum height, its VF will be 0. I suppose I should put 22 meters per second up. Acceleration, because this is vertical, is due to gravity. So 9.8 meters per second squared down. And we need the same direction, so I'll flip that to negative 9.8 meters per second squared up. The height is the same as the vertical displacement, so that's what we're trying to find. Looking at these variables, best equation to use, VF squared equal VI squared plus 2A delta D. Substituting in, Working this out, we get 0 equals 484 minus 19.6 delta D. Take the 484 to the left, we get negative 484 equals negative 19.6 delta D. Dividing by negative 19.6, going to 2 sig figs, we get a maximum height of 25 meters.